Hi, and welcome to our discussion of drainage divides. The next segment when we're talking about rivers and streams. We'll talk about the concept of what a divide is, and then we'll look at sort of large scale or think about large scale and large and small scale divides. And then we'll talk a little bit about river discharge, which is the byproduct of collecting precipitation as part of the hydrologic cycle over certain catchment areas. So the drainage divide is this high ridge right here, and what you find on this ridge is that you see the ends of streams reaching to near the top of the ridge, or this high spot, as you come up to the high spot here and then down the backside here. You see smaller streams or tributaries near the top, and as you flow down, branches converge and to make larger rivers and streams. This divide is really just a high spot, and it doesn't have to be very high. It could be 20 feet high over a region. It could be thousands of feet high, and I'll kind of explain that in a minute. It doesn't take much of an elevation change. It just changes the direction of slope. So here the slope is off to the right, and here it's off to the left. So any raindrop that falls right here is going to end up in this river system. Any raindrop that falls right here, as long as it doesn't evaporate or infiltrate, so on, as part of the hydrologic cycle, is going to end up in this river system. Okay, so the whole area that makes up the region that focuses water into the river system on both sides of this, okay, so one side and the other side, they're different. We're going to call that the catchment area, okay, or the drainage basin. So this entire area in here, okay, which is closed off by high spot all the way around, is the drainage basin. And everything that falls with regard to precipitation that falls in this region will be either infiltrate into the ground, evaporate, be picked up by plants, or whatever's left over is going to run off into the river system on this side, and then whatever falls on this side will run off into the river system on this side of that drainage divide. At the large scale, we have a system of divides that is based on mountain ranges. Now, I told you a divide could just be 20 feet high. It doesn't have to be a mountain range, but we do have major divides. And so you get an idea of what I'm talking about here. If we look at the Gulf of Mexico, here's the Mississippi River down here at the bottom. It's just charging right there. It's collecting water all throughout this region here, okay, that's in this central sort of mustard color, right? It includes the Missouri River and the Mississippi River, right? All running down here to essentially drain all the water that flows or that collects in this region. Now it's subdivided into two sort of smaller basins, okay? So here we have one larger river, okay? It's part of this drainage basin. All the water is flowing like this into this river. It's draining into the Gulf down there. And we have another basin over here, okay? And another river that's draining this region, and it's draining down into the Gulf right there. Okay? The whole region is separated by two mountain chains. One is the Appalachian Mountains, which is here, and the other is the Rocky Mountains, or the Cordillera, which is over here. Now notice where we are. We're actually very close to a drainage divide sitting right there at the end of Lake Michigan. Okay, so normally none of our water would have flowed naturally out into the Mississippi River, but we changed that by changing the direction of flow of the out of Lake Michigan. Okay, and now there's a big lock here, like a dam that keeps the water in the lake. But we have changed the direction of flow and redirected water out down the Mississippi. So we sent all our trash, dirty water, trash water, down that way. So the Chicago River is flowing not back into Lake Michigan, but down into the Mississippi right now, and that's artificial. Other interesting features, notice there's a drainage divide right here through Florida. Notice no mountains in Florida. Florida is totally flat, so it's a very subtle change in elevation where water flows to the east side or water flows to the west side. Another interesting feature is a divide that is circular here. This is called the Great Basin. There are no outlets here to the ocean, so that all the precipitation that falls in this region, if it doesn't evaporate or infiltrate, is going to actually run off into the Great Salt Lake, which sits down here by Salt Lake City. And the interesting thing about closed basins like this is that they usually have, because they don't have an outlet to or a source of fresh water, all that salt gets concentrated and will make a salt lake. And there are a number of places in California where there are smaller salt lakes, but the Great Salt Lake and the Bonneville Salt Flats is probably one of the most famous. Okay, now the pattern of drainage is going to change based on the sort of topographic features in the surface of the earth and the kinds of rocks and how they erode. If you have horizontal strata like you have in the top left here that erode equally everywhere at the same rate, so horizontal layers like this, okay, you're going to end up with this dendritic pattern. Dendritic simply means branching, so small branches or tributaries connecting to larger trunk streams and then to rivers and so on. Okay, if you have bedrock on the right hand side that has a series of fractures in it, the fractures are easier to erode than the solid rock, and so the river or stream will tend to stay in that fracture and to exploit that fracture, okay, following a pattern. This gives us, in some cases where we have joints, fractures that aren't really faults, they're just cracks in the rock, a pattern of joints will give us a rectangular drainage pattern. Okay. Radial pattern down here in the bottom, this one should be a no-brainer. You have a crater up here, you've got a volcano down here, okay, so you have water running off in all directions. The volcano itself builds up a mountain pretty fast, usually much faster than a river or stream can erode, and so it's going to change its drainage pattern as it grows. It's going to go from, one of these, a branching, which if you look at the volcano, you'll see that this section here and this section these little basins here, okay, they're really dendritic, okay, but the overall pattern on the volcano is radial. And then the last is something called a trellis system, and the trellis system works in this way. We see folded layers of rock. Some are easy to erode and some are tough. So you see the cliff former, a cliff former here, and a cliff former here. The cliff former is tough to erode, and so the river or stream will tend to stick to the soft materials. It sits in the valley, and then it has a dendritic pattern that comes down into the river or stream, into the trunk stream here. Okay. Now you see what's called an antecedent stream right here, which is a river that was present probably before this set of ridges formed, and it just cut right through because of its erosive power. So the trellis part of this is a series of dendritic patterns, so smaller dendritic patterns organized in this sort of rectilinear shape, right? So a ladder type shape might be a better explanation for it. Okay. Now, all those streams are going to converge to make bigger rivers and streams, and are going to have some amount of discharge that comes out of the catchment basin. And if you remember what I said, this whole area here, the total amount of water that's running off out of this region, which we'll call the catchment basin or catchment area, either one is fine, drainage basin, like this whole thing, right, should be the sum of everything that's entering into the Gulf of Mexico. So presumably, if you could take all the major rivers entering into the Gulf of Mexico, here, the Mississippi, and this river over here, you're going to get the total runoff, right, from this region. It should be entering in here. Now, it's complicated by weather and regional patterns, which, we're covering lots of lines of latitude here, so that means we're covering lots of significant climate variation from the top of the U.S. into Canada down to the Gulf of Mexico. But in principle or theory, that's how it should work. Okay? So that discharge that comes out of those rivers has to be measured, and we measure it using two different types of units depending on what you're asked for, who your client might be, cubic meters per second or cubic feet per second. And we measure this in several ways. The first way is we actually have to measure the velocity of the stream. So we measure that just like you'd measure the velocity of your vehicle, your car, feet per second. Okay, feet per second would be like putting a stick or a straw here, measuring how far or how fast it goes downstream. We'll get some distance in feet per second. We simplify it per second. Here, this one is 3.1 feet per second. This one is 1.5 feet per second. The next measurement we need to make is the cross-sectional area of the stream. Now, all streams are going to have a slightly different shape, and we have to account for that. But in this case, they're like approximated by a kind of a square or a polygon, trapezoid, if you will, and then a smaller sort of rectangle down here. So the area here is 1.5 feet by 59 feet. It's 59 feet across, 1.2 feet deep. So 59 times 1.2 gives us 70.08 or 70.8 square feet. So the cross-sectional area is 70.8 feet squared. The velocity is 1.5 feet per second. So cross-sectional area times discharge. Okay. They do that right. They forgot the units here. Okay, this should be feet per second, and this should be feet squared. But basically, you get the idea, feet per second. So it's going to be 70.8 feet squared times 1.5 feet per second is going to give us 106.2 cubic feet per second. The same type of calculations here. We have the velocity. So that's 3.1 feet per second, right? 3.1 feet per second. That's important. Okay. Oh, sorry. I'm getting ahead of myself. that calculation is down here. They actually put the seconds in. It's 3.1 feet. So it's 3.1 feet deep times 82 feet. It gives us 254.2 feet squared. They messed up the units here. Okay. That's squared feet, not cubic feet, right? And so that's the area here, okay, of this little trapezoid of water. And then we're going to multiply 254.2 squared times 3.1 feet per second. 3.1 feet is the velocity. So velocity times cross-sectional area gives us cubic feet per second that pass this point right here, or cubic feet per second that pass this point here. So discharge, D, is equal to cross-sectional area times the velocity of the stream. One other thing to think about when we're talking about the velocity of streams is something called the wetted perimeter. I'll talk about some of the features that affect stream velocity later on. But the wetted perimeter refers to this area, sorry, this surface area right here. We could just think of it as a line in cross-sectional area, and this line right here. Now you could have two streams that have the exact same discharge, right? The same cross-sectional area, I should say, same cross-sectional area. Okay, so here to here and here across here we have the same area, but they have totally different velocities, and one of the variables or factors is the wetted perimeter. The more friction we have between a particular body of water and the rock below, the larger the surface area, we're going to have more friction. So in this case, the wetted perimeter, if we were to measure along this line with a ruler, right, in real life, it'd be 19 meters. And if we would measure the wetted perimeter down here along this line, which is sort of low and flat, okay, it would be 32 meters. The longer the wetted perimeter, the more water is in contact with the surface, and so we're going to have a lower velocity. Okay. All right. So that basically sums up some of the concepts that we want to think about when we think about river discharge. Discharge is going to be cross-sectional area times the velocity of the river or stream. We talked a little bit about drainage basins. Okay, these are areas that are going to focus that water. So at the mouth of the Mississippi, we should be able to make a measurement of the water that's running out of the system and work that backwards into our hydrologic cycle to figure out how much water infiltrated, how much water ran off, how much water was lost to evaporation, and so on. Okay. Next, we'll move on to talk about parts of streams. We'll talk about erosion in streams, deposition in streams, and then finally kind of stream evolution as well. Okay.